take the cosine of 210 degrees, and you'll get minus 0.866. So notice we have a minus number. It's a minus number over here, the x value. The y value, take 210 and multiply, take the sine of that angle, and we get minus 0.5. So the y value is a minus number 2. Okay, that's in the third quadrant. In the fourth quadrant, let's pick an angle here. Let's pick 330 degrees. 330 degrees. So if I take 330 degrees and take the cosine of that angle, I get 0.866. So the cosine of that angle is this, like 0.866 right here. If I take 330 degrees times the sine of that angle, I get minus 0.5, which means that this is the y value, that these two angles have the same y value. I purposely picked it that way. So this gives you an idea of that when you're in quadrant 1, 2, or 3, or 4, your x values and y values, your sines and cosines, will switch between positive to negative depending on what quadrant you're in. So whenever you get confused, draw a circle like this, draw the angle that you're talking about, and you can figure out which quadrant you're in. Okay, I hope that's clear. Okay, now we need to talk a little bit about, we need to talk more about the tangent function. Suppose I have, I'm going to draw a xy graph. Here's the origin. Okay. Suppose I have a point out here, and this is 0, 0, the point, there's the origin 0, 0, and I have a point out here that's, and I'm just going to make this up, that's 5 units out here and 6 units here. Okay, and I'm going to draw a straight line to that. So this side over here is 5, the length of this is 5, and the length of this is 6. Okay, so, and the question is, I want to know what is this angle right here and how long is this? Okay. Well, I can figure out how long it is by simply using Pythagorean's theorem. This hypotenuse, Pythagorean's theorem, remember, x squared plus y squared equals r squared. So I would have 5 squared plus 6 squared equals r squared. So r is the square root of these. So I take 25, 5 squared is 25 plus 36, and I take the square root, and this is 7.8. Now what about this angle? Remember the tangent function. The tangent of the opposite over the adjacent, or y over x, is 6 over 5. 6 over 5. Whoops, I forgot. So the tangent of that angle. So in order to find out what this angle is, what I do is I take what's called the inverse tangent function. So I can rewrite this and say that the theta is equal to the, and we write it this way, inverse tangent of 6 over 5. And this is just typically how we write it. Sometimes for calculator, you'll see this little button, or it will say inverse tangent. Okay, so on my calculator, I would do this. I would say 6 divided by 5 equals, and then I say some calculators say inverse tangent, some will say arc tangent. Mine says arc, so I go push the arc button and then the tangent button, and this comes out to be 50.2 degrees. Okay, 50.2 degrees. Now, notice something very important with your calculator. You should be able to switch in your calculator from degrees to radians. Okay? I'm going to go ahead and switch mine. I've now switched from degrees to radians. If I do this same function, I'm going to do 6 divided by 5, and then arc tangent, I come out with 0.876. But now this is in radians. Okay, so it's done the same conversion, but now instead of giving me the answer in degrees, it's giving me the answer in radians. Obviously, they're very different. You have to know whether you're dealing with degrees or radians. So, for right now, we're going to do most of our computations, at least in this chapter, in degrees. At least I think we are, if I remember right. Later on, I believe we'll be switching more to radians, but for right now, I think this chapter is primarily working in degrees. Okay, now I'm going to talk just a little bit about adding vectors and and we'll do some homework problems on this. If I have, suppose I have two vectors. I have vector A, and then I have vector B, and A and B. This is the x-axis, that's the y-axis. Okay, there is a graphical way you can add vectors. Okay, and we'll there are two ways you can add vectors. There's a graphical way, and then there's a algebra way. What I'm going to do is I'm going to say that this A vector is made up of two components. There's a component here. Let me get rid of this one. The A vector is made up of, I'm going to say, write this a little bit bigger. This A vector is equal to this component here. I'm going to write this as little a, and if I drop the perpendicular down this way to B, well, I'll do it this way. I'm going to say A sub x and A sub y. Actually, I like this better, A sub x and A sub y. So what I say is that the A vector, this vector out here, has two components to it. It has an x component and a y component. And these two components are orthogonal. The word orthogonal, we're going to talk more about that later. But it's a great word, orthogonal. I just love how it sounds, orthogonal. But basically, two vectors are orthogonal if they're at right angles to each other. That's the easiest way to explain it right now. There's a much more strict mathematical definition. We may talk, if we have time, we'll talk about it later. But for right now, two vectors are orthogonal if they are at 90 degrees to each other. Doesn't matter really how they're oriented. as long as they're at 90 degrees to each other, these two vectors are orthogonal to each other. Well, turns out the x and the y-axis are, by definition, orthogonal because they're at right angles to each other. So, when we write a vector, we break it up into its orthogonal components. So that would be ax, a sub x, and I'm going to put a little x with the hat over it, and what that is a little unit vector length of 1 in the x direction. That's just to show you what direction is going. Really, this is really just a direction indicator that this a sub x is in the x direction. And the y component is a sub y in the y direction. So this signifies a unit vector in the x direction. This signifies a unit vector in the y direction. Okay. If I have two vectors, suppose I have two vectors in A and the B, I can do the same thing. I can do the same thing to the B vector. I can break this up into its components, bx and by, and I can say that the B vector equals the bx component in the x direction plus the by component in the y direction. Now when I add these vectors, okay, I would say, I'm just going to write it like this, a plus b, and I'm going to call that a new vector. I'll call it c. That is, the new vector c is a sum of a plus b. And when I do that, how do I add the components? The components I add up by simply add the components. So it would be ax plus bx, all heading in the x direction, plus ay plus by, the sum of those, all heading in the y direction. Okay? So if I do this, so that's how we add it up algebraically, and so I would say that the new vector c is cx in the x direction plus cy in the y direction, where ax plus bx is cx and ay plus by is cy. Okay, that should be pretty obvious. To add these vectors up using geometry, I'm going to have to do this over here. What we do if this is A and this is B, what we do is we take one vector, it doesn't matter which one, I'm going to take this one and slide it. If this is the head of the vector and that's the tail of the vector, I slide one tail up to the head of the other. So I'm going to take this B vector and slide it up without changing, I can't change the angle, but I slide it up and put it right on here. So if I do that, let's see if how I can do that. Actually, what I should do is I should measure the length of it to make sure I get the right length. It's about 9 inches at that angle, so I move it up here, whoops, adjust it down a little bit, about 9 inches, and I move it this way, and I draw a line about 9 inches tall. Now this is vector B. I just slid it up, and I put the tail of B to the head of A, And then I draw my new vector. My new vector goes from the tail of one to the head of the other. So my new vector is this vector, that's B. My new vector is this one, C. So basically, I can say that A plus B equals C. So the C vector is a brand new vector, and it goes from here to here. Now notice it shouldn't make any difference whether I added A first or B first. For instance, I could take the A vector and slide it. Instead of sliding the B vector, I should be able to take the A vector and slide it. So if I take the A vector, oh, that's about 11 inches long, and slide it up this way, that's about right. It comes right to about here. So I can also slide the A vector up to show that actually I can change the order here. B plus A is still C. The order that I add the vectors up in a geographic way shouldn't make a difference, and in fact it doesn't make a difference. Okay. At this point, I'm just going to just talk a little bit, very briefly, in general about vectors in general. Remember, we talked about orthogonal functions. What do we talk when we talk? We can talk about a multidimensional vector. In fact, we can talk about a vector. Let's say the vector A has a x component. I'll just say ax plus a y component in the y direction, plus an a z component in the z direction. That would be a three-dimensional vector. Do we have to stop there? Actually, in order to visualize it, we probably do. It's hard I can't visualize a four-dimensional vector. But however, mathematically, there's no reason why we couldn't add another one. We'll call it AP, in the P direction. All we need to say is that mathematically, that the P vector and the Z vector and the Y vector and the X vector are all mutually orthogonal to each other. So mathematicians come up with multi-dimensional vectors, 5, 10, 20, however many dimensions you want, as long as each dimension is mutually orthogonal to each other. As an example, when you get to the lecture just before Christmas, when you do a little lecture, it's not in the book, but it's a little lecture on Einstein's theory of relativity, we'll see that Einstein based some of his theory, whereas another physicist came by just called Minkowski, and he developed what's called Minkowski space. What the heck is that? Minkowski is just the name of the physicist who kind of dreamed this up. But it goes right along with Einstein's theory of relativity. Minkowski space is a four-dimensional space. Okay? And the four dimensions are x, y, and z, and then there's a fourth dimension. And that fourth dimension is time. But it's not exact. In order for Minkowski to work out the mathematics just right, and he was working with Einstein, or he was working off the physics that Einstein had started, in order for Minkowski to get the physics of this right, mathematically, he had to do something a little bit unusual, and he had to say that the fourth dimension, mathematically, had to be the square root of -1 times the speed of light times t. So actually, this, in Minkowski space, and in Einstein's theory of relativity, this is four-dimensional space. X, Y, and Z, which are regular three-dimensional coordinates, and the square root of -1, which we can sometimes call I, C, which is the speed of light, times time. So actually, the Minkowski space is actually we might say it's complex. In other words, it uses complex numbers. But this is and the mathematics is way beyond what we're doing here. But this is just to give you an idea that physicists do talk about multi-dimensional spaces, and the first one to really do that was this guy by the name of Minkowski, and it's used in relativity all the time. Since then, they've developed higher dimensional spaces for things like string theory, but that's way beyond this discussion. Okay, at this point, what let's do is let's go over, we're going to go over, directly go over some of the problems. We're going to go over some of the problems right now, and with the hopes that this will give you some good understanding. If you turn to page, well, this will give you a good understanding of how to apply these trig functions, etc. Okay, I'm on page 102, and question number one. Question number one, we always define the angle of a vector relative to what? Well, normally, the normal way of doing it, if we're talking about two-dimensional space, x and y, is if this is x and this is y, our angles are always relative to the x-axis. So like that's 120 degrees. We start from the x-axis and we rotate out. So, or maybe the angle's over here. We always start from the x-axis. Now we can have negative angles. Suppose we have this angle. We could say like it's negative 70 degrees. Or we could say that that angle is the same thing as this angle, which would be, what would it be? It would be 260, it would be 290. Because basically 360 minus 70 is 290 degrees. So basically an angle of 290 degrees is the same as the angle of minus 70 degrees. Okay. Okay. I'm going to skip question number 2, and if I have a vector, it's question number 3, directly in the y direction, is there any x component? No, the x component in this case is 0. There is no x component. So, okay. Okay. Well, let's go back and do number 2. Okay, number 2. For the following observables, tell whether they would represent the magnitude or the angle, or whether they would be represented by the magnitude or by the angle of the vector. The speed. The speed is representative of the magnitude of the velocity. Okay, the heading. The heading is like the heading of a vector. Vector A would be this angle. So that would be the angle, represented by the angle. Direction. Direction is also what angle you're going. Distance. Distance would be a magnitude. Okay. Question number 4. If on page 102, if a vector has an x component, if the x component is negative, and the y component is positive, which quadrant are we in? If we're all you have to do is just go x that is negative and a y that is positive puts you over here. You're in the second quadrant. Okay. If you are using equation 3.3, well, now what's equation 3.3? Guess I have to refer back to what equation 3.3 is. Equation 3.3 is that an angle? Question, this one here. Okay. How would you if you were using this equation, suppose, well, this is a good problem. Suppose you had an x of -2 and a y of 4, so you're up here. And we want this angle here. So we have an x of -2 and a y of 4. Okay? So we come in here and we say we want the inverse tangent of a y of 4 and an x of -2. Now, okay, we may go over this a little bit. If we do this on our calculator, and if I say 4 divided by 2 negative, I obviously get -2, right? So this will be the inverse tangent of -2. I now say arc tangent, inverse tangent, and I get, what do I get? And I get an angle, at least on my calculator, of -63.4 degrees. Goodness, what happened? Because when you look at this, always think about this. When you look at this, you think, oh, something's wrong, because this angle should be positive angle, but I'm getting some kind of angle like this. I'm getting like an angle that's minus 63.4. Okay? What's happening is that the tangent function, when you put a minus at if one of these is minus, it thinks you're over here in the fourth quadrant. The tangent function does, the way it's calculated on a calculator. So it thinks you're in the fourth quadrant, and so it's drawing the angle like this of -63.4 degrees. Well, obviously that's 180 degrees opposite. I need to be over here. Okay, so there's two things you can do, a couple things you can do. One thing is, whenever you do this, realize, draw what quadrant you're in. You have to know that you're in quadrant 2. To do that, you have to know the x is negative and the y is positive. This point, it clearly is in quadrant 2, although the calculator is giving you an angle like you're in quadrant 4. Okay, so you have to be smarter than the calculator, and you have to realize this isn't right. What I have to do is I have to add 180 degrees to this. So I take basically I add 180 degrees to this, and I get 180 minus 63.4, and I get 116.6 degrees. Okay, so now, is there another way to do this? Absolutely there is, and this is the way I prefer. The way I prefer to do this is this. I calculate this angle here. Say I calculate okay. Is that right? Let's see, calculate this tangent. Well, maybe I shouldn't confuse you. This is probably the best way to do it. What you need to know is that well, let me say this. Okay, there is another way to do it. Suppose, I'll show you this. Suppose I draw this angle here, theta. This tangent of this theta here is this over this. So ignore for the moment this is a minus number and just say this is 4 over 2. And I take the inverse tangent of this. So all I'm doing now is just supposing I'm going to ignore for the moment I'm in the second quadrant, and I'm just going to look at this angle over here. The tangent of this angle is the opposite over the adjacent, 4 over 2. So I get the inverse tangent of 2, 4 over 2, 2 inverse tangent, and I get 63.4 degrees. So that's this angle here, 63.4. But what do I have to do? I have to take that. See, this angle here, that angle here, is 180 degrees minus 63.4. Here's 180, and I subtract this angle here, and that gives me this angle here. This is what I'm really looking for. So notice that gives us the same answer as before, 116.6. So there's several ways to make sure you get the right angle you want.